Hello everyone. Let us start chapter 19. Chapter 19 is about vibrations and waves. Okay. I want to start from the Hooke's law. I have a spring. Okay, this is the spring. So you can draw like, let us suppose this is the spring. This is the spring. I do not count the mass of the spring. Okay, I ignore the mass of the spring. Right now there is no change in length of the spring. Now if I attach the mass, I have a weight here, mass. Okay, mass half kg. If I attach here, then look at this, the length of the spring changes, of course. You see this mass is at rest right now. We call equilibrium position. Okay, no motion, just it is at rest. Okay, so if I attach the mass right here, if I attach the mass right here, what happened is the length of the spring changes. Length of the spring changes. So I attach the mass here. Okay, this is the mass. In this case, I have a half kg only. So now what happened is, this is the mass attached. So what is your change in length? Change in length is from here to there. So this is your change in length. Let me call change in length is x. X is the change in length, downward direction. Okay, look at this. Look, this is a spring and I am going to attach the mass right here. Now the length becomes longer. So x is the change in length. For example, if this length from here to there, if this is, let's say, 40 centimeter, and if this is, let's say, 50 centimeter, so what is your x then? What is the change in length? So change in length is x equal to 50 centimeter minus 40 centimeter is equal to 10 centimeter. This is your change in length. Okay, so here no change, 40 centimeter. Now if I attach this, let us suppose I am not measuring here, I just give you some number only. So this is 50 centimeter. I consider that only. Okay, I am not measuring here. You can use a meter stick to measure this if you want the exact data. Okay, so look, the size of the spring change. Now it becomes longer. I attach the mass here and the spring is longer now. Think about this point. If I remove this mass, it goes back to its initial shape and size. If I attach this mass, okay, it goes down. Now if I remove this mass, this point, this hook, it goes back to its initial position there. So if you need a force to pull it down, you attach the mass to pull it down, to change the length. Now what force bring this point back to the initial position? So there is some force created inside the spring. We call that spring force, or you can call it restoring force also. So look, this force mg pull the spring, like change the length of the spring. Due to this force mg, the spring is extended here, elongated. But there is another force in upward direction. This force, upward direction. This force restore the spring. If you remove the attached mass, this force we call spring force Fs. This restoring force, or is spring force or restoring force, that's the same thing. This force restore the spring. That is why we call the restoring force also. Restoring force, or you can call spring force. That's the same thing. Spring force. This is the same thing. You can write down Fs. Okay, Fs. Okay, now look at this. Here Fs is upward direction, so Fs is upward direction. Mg it is downward direction, Mg downward direction. And look, that is the net force. Fs minus Mg is the net force acting on the object M, mass M. Fs upward direction, Mg downward direction, but the object is at rest. If the object is at rest, definitely there is no net force. The object is in equilibrium. So this is F net force. But since the object is at rest, the net force is 0. This is 0. So Fs minus mg, this is equal to 0. So simply you can write down Fs, spring force is mg. So the spring force or restoring force is equal to the weight of the attached mass. So if the mass is in equilibrium, and this restoring force, there is a Hooke's law, the restoring force Fs, Hooke's law is within the elastic limit, the restoring force, or you can write down spring force also, the restoring force or spring force is directly proportional to the change in length of the spring. Okay, that means you can write down here the restoring force Fs is directly proportional to x. X is the change in length of the spring. But here I use the word within the elastic limit. What is elastic limit? Is, look, no change in length. If I apply the force downward direction, and if I release, it goes back. I increase my force, the extension is more, and if I release, it goes back. I increase my force, look, the change in length is bigger, and if I remove my force, it goes back. But if I apply really big force, a point will come where this spring permanently deformed. Like if I apply really, I am not going to do this. If I apply really big force, a point will come. If I cross that point, then the spring cannot go back to its initial shape and size. That point is called as the elastic limit. So this law is applicable only within that point. We call that elastic limit. So within the elastic limit, the restoring force or spring force is directly proportional to the change in length. And this one you can write down like this. The proportionality sign here, this is, if you want to put equal sign, write down F equal K, uppercase K, X, but put the negative sign. Why negative sign? Look, Fs is upward direction, X is downward direction, always. Fs is not always in upward direction, but Fs, restoring force, and X, they are in opposite direction. If you compress the spring up, like if you push the spring up, restoring force is downward direction. If you compress this up, so X is up, restoring force is down, then in that case. So the Fs and X, they are always in opposite direction. To indicate that opposite direction, you put the negative sign, and this is the Hooke's law. And K here, this K we call spring constant. This K, this is called as the spring constant. Okay. And if you keep the spring in this position, the second position, the spring store the energy, because this force does some work, spring does some work, and this spring stores some energy. We call that elastic potential energy, PE, and elastic potential energy formula is 1/2 kx square. This is a formula to calculate the elastic potential energy. X is the change in length of the spring, K is the spring constant which is given, and the different spring, they do have a different K. This, you can measure the K. This spring has a K, spring constant. If you bring another very big, strong spring, that spring has a big K then. Okay, so the different spring, they have a different K. Now the concern here is vibration. Okay, vibration. This position is equilibrium position. Now if I pull this mass from here, but a little bit down, and let it go, now this mass is vibrating, the mass is oscillating, move up and down. If I set the spring horizontally, I can do this right here, and in that case the mass oscillate like horizontally back and forth this way. Okay, so this is the vibration. Okay, so this is the equilibrium position, this is the at rest, this is the equilibrium position. If you displace from here then let it go, then it vibrate about the equilibrium position, we call that mean position. Same as, look at this, it is easy. I have another one, we call this is a pendulum. That the one I talk about was spring, and this is a pendulum. Now here also this is a pendulum, and if I release from here, it vibrate. This is the vibration, oscillation. And here what I need to do is I have to calculate the time period. Okay, so if you do the pendulum, do you know what is pendulum? We call simple pendulum. There are different types of pendulum: simple pendulum, physical pendulum, ballistic pendulum, torsion pendulum. There are different types of pendulum, but we do only the simple pendulum here. Simple pendulum. So what is simple pendulum? Simple pendulum, this is the simple pendulum. This is your simple pendulum. So this is a thread, this is a thread, but we ignore the mass of the thread. Okay, and you have a ball here, this ball. This is a heavy but is small, we call heavy point mass. This is a heavy but it is small, the size is volume is small but it is heavy, it is a steel iron. Okay, and so heavy point mass suspended by the light thread, light rope. The mass of the rope is negligible and it is free to oscillate. This is called as the simple pendulum. Okay, so heavy point mass suspended by light thread and free to oscillate, no friction there. It's called simple pendulum. A heavy point mass suspended by the light thread and this mass is free to oscillate, no friction. We ignore the friction. Okay, that is called as the simple pendulum. And here let us suppose L be the length of the pendulum. L this is the length of the pendulum. Length of the pendulum. Length of the pendulum. Okay, look at this. This is my pendulum. I can measure the length, and if I release, I hope you can see this. If I release, here I have to calculate the time period. What is time period? Look at my hand. I release the ball from here, I mean this pendulum from here. You start your timer. You can start your timer, okay? Clock. Exactly at the same time. Stop. Whatever time you get, that is the time period. That means time taken to complete one oscillation. Look here, what is one oscillation? This is one oscillation. You release, don't move your hand, okay? This hand. This is one oscillation. This time taken to complete one oscillation, that is called as the time period. This, in case of pendulum, one oscillation, that is a time period. We are talking about the simple pendulum. We talk about the circular motion, time taken to complete one circle there. We can relate this circular motion and the pendulum also. Okay, so in this case, time taken to complete one oscillation, that is called as the time period of the simple pendulum. Okay, time period T. This is time taken to complete one oscillation. Time taken to complete one oscillation, that is called as the time period. And the time period of simple pendulum T, this is represented by T, this is equal to 2 pi square root L divided by z. T equal to 2 pi square root L over z. What is L? Length of the pendulum. What is z? Gravity, 9.8 meter per second square. So now we can see here the time period of the simple pendulum. It depends on length of the pendulum only. Here I have, let's say this is 50 gram. If I bring another object having mass 100 gram, still the time period is same. As long as you have the same length, time period is same. Because the time period depends on length of the pendulum and gravity only. If you measure the time period of this pendulum here, let's say 1.5 second. If I change this mass, don't change the location, this room, don't change the length, okay, but simply change, this is 50 gram, now make it like 100 gram and do the time period, you get the same thing, because the time period of the simple pendulum is independent of mass, but it depends on length of the pendulum and it depends on gravity. For example, this pendulum here, let us suppose time period is 1.5 second. Don't change the mass. If you take it to the moon surface, what happened? Do you still get the same time period? Everything remains same. Like look, same length, same mass, everything same. But you change the location from here. I'm here in the room, this room, DVC, Pleasant Hill. But if you go to the moon surface, what is changed there? Gravity change. So the time period change. Right? But if you change the mass has no role, because look at this formula. The time period is 2 pi square root L over z. So the time period depends on length of the pendulum, time period depends on gravity. Okay, so please note this, that is important. Okay, so this is about the vibration, and then if you know the time period, then you can calculate the frequency. What is frequency? How many oscillation you can make in 1 second. That is a frequency, number of oscillation per second, that is frequency, and frequency is 1 over t, 1 over time period. And the unit is, what is the unit of frequency? It is hertz. You can write down Hg. The unit of frequency is hertz. So in case of simple pendulum, just plug this time period here. Plug this time period here. What happened then? You get your frequency is frequency f. This is equal to 1 over time period. But time period is 2 pi square root L over z. So your frequency f equal to 1 over 2 pi square root z over L. This is the formula to calculate the frequency of the simple pendulum, and the unit is hertz. Okay, so this is the vibration of simple pendulum. We have this in this case also. This is not in our syllabus, so I am not going to do this. This object is vibrating. Here also we can calculate the time period, time taken to complete one oscillation, that is the time period. And in this case, in case of we call mass spring system, in case of mass spring system, the time period is different. We cannot use that formula. Okay, in this case the time period depends on mass, the oscillating mass, and the spring constant. In case of spring, the time period depends on the attached mass and the spring constant. Actually, it is the time period of the mass spring system. This system is equal to 2 pi square root m over k. Like a mass spring system, this. If you attach the mass, we call this is oscillating mass. Okay. In this case, if you want to calculate the time period t is equal to 2 pi square root m over k. This is the formula, but don't worry about it. Just do the simple pendulum. Okay. So this is about the vibration. Okay. If the object is vibrating, then the wave is generated there. Wave. So what is wave? Think about the like a lake, swimming pool, pond, whatever. Let us think about the swimming pool. Okay. And if you take one rock, stone, and if you throw there, you disturb the water there. The water in the swimming pool is still water at rest. You throw there. You throw the rock in the swimming pool. Then you can see the ripple. We call that is a wave. You know that, the ripple, right? Like this, ripple. That is the wave. But how did that wave produce? You throw the rock there, you disturb the medium. The medium there is water. So simply wave, I do not have a very solid definition, but you can simply say that wave is a disturbance. Okay? If you disturb the medium vibrates, then wave generated there. And there are two types of wave. One is transverse wave, and another one is longitudinal wave. Transverse wave and longitudinal wave. So what is transverse wave? Look at this. The transverse wave, I can use this string. This string. Do you see any wave here? Do you see the wave? I don't know if you see it. You can see this. This is transverse wave. This is transverse wave here. This is transverse wave. So what is transverse wave then? Okay, the transverse wave is, let us suppose the wave is propagating in this direction. This is the direction of wave propagation. Direction of wave propagation. And what is this? This is the string, and the wave it goes something like this. Okay. So what happens is there are thousands of particles here, string particles like this, string particles. Okay. You don't have to draw this right now. Okay. So what happens is the particle vibration is up and down, up and down, up, down, like this. So the particle vibration, this angle is 90 degrees. In transverse wave, the particle vibration is perpendicular to the direction of propagation of wave. Okay. In transverse wave, the particle vibration is string particle in this example. Okay, the particle vibration is perpendicular to the direction of wave motion, or you can say wave propagation. So that is a transverse wave. And what are the example? This is the transverse wave. The string wave is a transverse wave. This is the transverse wave. So you can write down a string wave. Example is, like one example is string wave. Another one, you can write down the ripple, the water wave. Ripple is also the transverse wave. Like you can think, like I said that in transverse wave, the particle vibrate up and down, and wave propagate to the right or to the left. You can think about like a pond, like this. Let us suppose this is the pond, lake, swimming pool, whatever. This is, here you have water. This is water here. Okay, and this is shore. What you can do is you take one leaf, dry leaf, like something like this. Dry, okay, very light, dry leaf. And first gently put the leaf on the surface of the water. Okay, so somewhere there, you put the leaf somewhere there, and take one rock and throw the rock right here. Then wave generated there. The leaf here, water is still water, okay, at rest. Do you think the leaf, it goes there with that wave? No. What do you see is the leaf is moving up and down only, but it never reached the shore here, because it vibrates up and down, but it never moved from here to there if there is no wind there, okay? If there is a strong wind, that is different. So simply the leaf move up and down, but it never reach the shore. Similar to this, because the particle vibrate up and down, only the wave propagate. Here the ripple, the wave go to the shore, but the leaf stay there, just vibrate up and down. So this is the transverse wave. So the example is steam wave is a transverse wave, ripple is a transverse wave, even light is also the light, it is an electromagnetic wave, but it is still transverse wave. So transverse wave, and another type of wave is we call longitudinal wave. What is longitudinal wave then? Any idea what is longitudinal wave? So longitudinal wave, the particle vibration is parallel to the wave motion. So for example, let us suppose this is the direction of wave propagation, and the particle is here like this. These particles, they vibrate like this, back and forth, this way, like this way. That is called as the longitudinal wave. So let me see. Do you know what is this? This slinky, right? So what happens is, if I have, let's say, how the particle vibrate is, particle it never vibrate up and down, not like this. The particle vibrate in this case like back and forth, this way. I can do in the vertical direction. In this case, the wave propagation is either down or up. Now look at this, how particle vibrate. Look, in the same direction of wave propagation. In the horizontal also I think we can do that. You see the particle vibrate something like this. One second, I need someone to help me, but I don't have. You can see this, the particle vibrate back and forth. It is not vibrating like this, up and down, not similar to the string. So this is called as the longitudinal wave. So longitudinal wave, I'm talking about the longitudinal wave. So what is this? This is direction of wave motion. Direction of wave motion, and here in longitudinal wave, the particle vibration is parallel to the direction of wave motion or wave propagation. That's the same thing, direction of wave motion. And the good example is sound wave. Good example is sound wave, okay? So we have two types of wave, transverse wave and the longitudinal wave, okay? Whatever wave you have, you can use this plotting to represent the wave. Wave is represented like this, both ways, this way. This is how you draw the wave. And here, this point, this is a peak, and here, this point, this is the minimum. This point is called as the crest, and this point is called as the trough. This is crest, and this is trough. And what is this line? This is the wave propagation direction, and this line here, the horizontal line, this line is like a equilibrium line, mean position, equilibrium line, okay? Now from here, what is equilibrium? Look at this. We can use this also. This equilibrium position is this. This is equilibrium position. Now if you displace from equilibrium position like this, you displace and release. Now it vibrates about the mean position like this, equilibrium position or mean position, that's the same thing. My hand here is a equilibrium position. Okay, so this is equilibrium position. Now if you displace from here to there, from here, this is equilibrium position, this is maximum, we call the extreme position right here. Okay, from here to there, the displacement is called as the amplitude. Okay, here or from here to other side also, this is also amplitude. So it is oscillating about the mean position, and the maximum displacement on either side, this or this is the amplitude A, this is also amplitude A. So what is amplitude? You need to know this. Amplitude, okay, it is simply denoted by A, uppercase A, okay, amplitude. This is the maximum displacement on either side of equilibrium position. That is called as the amplitude, and amplitude will always take the absolute value. Amplitude is always positive. Amplitude is always positive. Like here, do you know this wave? Is it sine wave or cosine wave? Any idea? This is sine wave. Sine wave always start from the origin 0, 0. Always start from the origin 0, 0. So for example, if you write down y equal to a sine omega t, something like this. If you write the equation, okay, y equal to a sine omega t, this is the amplitude. For example, if you write down y equal to 2 sine, let's say 7t, like this. What is the amplitude? What is amplitude here? Amplitude is 2, the unit is given like maybe meter, centimeter, like this. Amplitude is the displacement, so it is, I can write down meter, okay. So if y equal to 2 sine 70, it is 2 meter. What about this? If y equal to negative 2 sine 70, what is the amplitude here then? Negative 2? No, I told you amplitude is always positive. Here also amplitude is 2 meter. But this equation y equal to 2 sine 70 and y equal to negative 2 sine 70, how do you plot then? If you plot this equation 2 sine 70 amplitude, so first you have to go up like this, it is positive. If it is negative, this one negative 2 sine omega t, in this case it is, first you have to go down, this is 2, here this is 2, but both they are length, displacement, amplitude, we take the positive, okay. So amplitude, the maximum displacement on either side of the equilibrium position, and you know this, the crest is the peak, the trough is the valley, minimum, and like if the distance between trough and the crest, if this distance is, let us suppose 10 centimeter, the distance between trough and crest is 10 centimeter, what is your amplitude then? 5 centimeter. If this distance is 10 centimeter, amplitude is only 5. So please keep this in mind. Okay, and then another term you need to know is time period. Okay, so what is time period here then? What is time period? Time taken to complete one wave. One oscillation is one wave. So time period, the time taken to complete one wave. That is a time period. This, look here, you start from here, look at this. If you start from here, from this point, so count the one wave only. One wave is if you start from here to all the way up to there, up to here only. So this is the one complete wave. So whatever time you take, that is the time period. Time taken to complete one wave, that is a time period. And there is another term we call the wavelength. Wavelength. Wavelength is simply denoted by this symbol. Do you know what is this? It is a Greek letter. This is called as the lambda. Lambda, okay, lambda. So what is wavelength then? Now look at this. I want to erase this. What is this point? This is crest. What is this point? Another crest. Two successive crests. This length from here to this length is a wavelength. Or from here to there. This is also wavelength. So the distance between two successive crests or the distance between two successive troughs, that is the wavelength lambda. Successive, okay, from this point to this point, or from this trough to this trough. The distance between two successive crest or distance between two successive troughs. That is called as the wavelength, and it is denoted by lambda. So here we define time period, and here you can also define the frequency. Number of wave per unit time. Number of wave per second. That is a frequency. So frequency, you can write down simply F. This is number of waves per second. This is what we call the frequency. And you know that the frequency is 1 divided by time period. This is the formula. We already talked about it. Frequency is 1 over time period, and the unit is, of course, hertz. So time period, frequency, wavelength. Wavelength is distance between two successive crests or two successive troughs. And there is another term, speed of wave. Speed of wave. Okay, speed of wave. It is simply denoted by v. Any idea what is the speed of wave then? What is the speed? The distance divided by time, the rate of change of distance, that is a speed. So here we are talking about the wave. So simply your speed of wave is, you can write down wavelength lambda divided by time period. This is how we calculate the speed of the wave. Wavelength lambda divided by time period. That gives you the speed of the wave. So let me erase everything else here. I have to talk a little bit more about the speed of wave. Because from here you can get the numerical problem also. Now look at this. Speed of the wave v, this is equal to wavelength lambda divided by time period t. But you know that the frequency is 1 over time period. So this formula you can write down v equal to lambda times 1 over t. It is the same thing. So v wavelength is equal to lambda times f. So if you have to calculate the speed of the wave, you need to know the wavelength of the wave and the frequency. So using this relationship, you can calculate the speed of the wave. If the speed of the wave is known and if the frequency is known, you can also calculate the wavelength. Okay, you can also calculate the wavelength. Okay, so these are the terms you need to know. And there is another one. What happened is, we call the standing wave in the string. That this is a little bit difficult for you, so just quickly we call standing wave in the string. What is this? What is the standing wave then? Right, look at this. Let us suppose this is the valve, there is another valve, and there is a string like this. I can produce the standing wave. What is the standing wave? Just look here. I can call this is the standing wave. What happened? here is, if the wave, let's say one wave, you generate the wave from here and it goes like this. My diagram is not quite good. And from here, the wave from this point wave reflect and it goes this way. Something like this. Now look at this. This point is called node. This is also node. This is 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 node. And this point, and here, these all they are called anti-node. AN, that is anti-node. Okay, anti-node. Okay. What happened is right here the particle here vibrate with maximum displacement, which is called amplitude. Everywhere here, with maximum amplitude. But right here, the wave moving forward, that pull the object up, and the reflected wave pull the object particle down. So there is no displacement, and you see the wave look like steel wave at rest. That is called as the standing wave. And there is a different mode of the standing wave, and we can also calculate the frequency of the the different mode. Okay, but that is not necessary in this class. So you can see, if you read the textbook, you can see the standing wave there, but don't worry about that. We can calculate the frequency. Those who are interested, the frequency of any mode Fn equal to NF1. NF1, this is the formula here. F1 is the very first mode. We call that fundamental mode, which is F1 equal to, it is V divided by 2L. This is the formula. What is L? L is this length, the length of the string. This length, L is the length of the string. L, this is length of the string. L is the length of the string. And V is this is the speed of the wave in the string. V is the speed of the wave in the string, and we have a formula to calculate this also, but you don't need it. Okay, you don't need it. So if you know the F1, this is a fundamental mode, very first mode, which is V divided by 2L. V is the speed of the wave in the string, and L is the length of the wave. Then N is 1, 2, 3, 4, and so on. Okay, so you can calculate the frequency of the different modes also, but for you can ignore that. Okay, so this is about the string wave. And the wave, I told you that there is a transverse wave and longitudinal wave. One of the example of the longitudinal wave is a sound wave. Okay, sound wave. The things you need to know here is sound wave needs the medium to propagate. If there is no medium, sound wave cannot propagate. Okay, sound wave needs a medium to propagate, to move. So sound wave can propagate through the liquid, gas, and the solid, but their speed is different in different media. Okay, so if you want to measure the speed of the sound wave in the air atmosphere, you can use this formula: V equal to 331 plus 0.6 t meter per second. This is a formula to calculate the speed of the sound wave in the air, which is kind of important also. So T here, T is the temperature in Celsius degree. T is the temperature in Celsius degree. So if temperature is 0 degrees Celsius, simply the speed of the sound wave is 331 meter per second. But at 20 degrees Celsius, the speed of the sound wave in the air is, if you plug T equal to 20 here, you get 343 meter per second. Okay, sound wave 333 meter per second. That is the speed of the wave, sound wave in the air. And you know that the sound wave, it is 343 meter per second. This is the speed. Now think about the light wave. Light wave, the speed of light wave we simply represent by little c. This is 3 times 10 to the power 8 meter per second. Look how different. 343 only. This is 3 times 10 to the power 8 meter per second. This is really big number. That is why like a thunderstorm. First you see the lightning in the sky. You see the lightning in the sky, and after few seconds then you can hear the sound. Why? You see the lightning first. The reason is light moves faster than the sound wave. First you see the light and then you hear the sound, because sound travel only 343 meters per second. Okay, so speed of the light wave is way bigger than the larger than the speed of the sound wave. Okay, so in this sound wave we have to talk about the Doppler effect. I'll bring another video. Okay, so please watch the Doppler effect video. I'll post that. Okay, thank you.